Okay, so we were talking about exact equations and we didn't finish it. So what does it mean by exact equation? Okay, first we discussed the exact uh, differential. Okay, so if you have a differential m dx plus n dy where m and n are both functions of x and y, so we're talking about functions of two variables, x and y. They are both independent variables. If we can, rewrite this m dx plus n dy as full differential df or dz, where the differential of a function z equal to f is defined as partial f partial x dx plus partial f partial y dy. So if we can rewrite m dx plus n dy as a full differential dz, okay, then we say this expression m dx plus n dy is a exact differential. And in that case, we can easily solve a differential equation m dx plus n dy equal to 0, and to get the solution f of xy equal to c. Okay, where f can be found from the procedure as we showed last time. Basically, we have to use both m and n to find this f. Okay, so these are the formulas. Okay, so f will be the integral of m dx plus gy, where gy is determined from this equation. Okay, we're not going to repeat it. Then once we find the f, then the solution to the differential equation will be f of xy equal to c. Okay, so there are several steps that we need to follow to solve an exact differential equation. And we did one example to show the detailed steps last time. I'm not requiring everybody to memorize all the steps. You just follow the procedure I wrote in here. Do it step by step. Okay. So let's just do one more example of exact equations. So this example says when you solve the initial value problem, e to the x plus y dx plus 2 plus x plus y e to the y dy equal to 0, where the initial condition is given as y of 0 equal to 1. Okay. So obviously, this is not a separable equation. You cannot separate the x and y, obviously. The two sides of the equation, you cannot rewrite the equation to separate x on one side and y on the other side. So that's not a separate equation. And it's not a linear, equation. So we got the y times c to the y, That's not linear in y. So we cannot use the formula for linear first order differential equations. But we can check whether this equation is exact or not. Okay. So the first step to identify m, that's e to the x plus y. Okay, that's the function with dx, and n is another function that's 2 plus x plus y times e to the y. So that's the function with dy in the differential equation. Remember, a differential equation can be written either in the differential form or derivatives. Okay, they are equivalent. So if the equation is written in differentials of y prime, then you can rewrite the equation into the differential form. All right. So we got the m and n, then we just start to check whether this differential is exact or not by using the criterion, partial m partial y equal to partial m partial x. All right. So we just check whether partial m partial y and partial m partial x is equal. If they are equal, then that means this differential equation is exact. So if you take the partial derivative of m with respect to y, you treat the x as constant. So you're going to get a 1. Similarly, when you take the partial derivative of n with respect to x, you treat y as constant. So then you only take the derivative of x, you get 1 also. So you can see they are the same. So this criterion partial m partial y equal to partial m partial x is satisfied. So we can conclude that the differential equation is exact. Okay. Then we can use the formula before to find the solution of this equation. All right. And we need to find this function f, which is the integral of m plus gy. Okay, and the gy can determine from this equation g prime y equals n minus the integral of partial m partial y dx. Okay, and eventually when we find the function f, the solution to the original differential equation will be fxy equal to c. Remember, that's the last step. We still have this step, okay, to find the solution of the initial, the original differential equation. So let's just find the gy first. So first, we use this g prime of y equal to m minus the integral of partial m partial y dx. So n is just 2 plus x plus y e to the y, as we identified. And partial m partial y is just 1. We already did it. So basically, you just integrate the 1 with respect to x. Okay, remember? You have to specify which variable you integrate. So if you do that, you get x. So then, you just cancel x, and you get 2 plus y e to the y at the end. So that's g prime. And then you can find the gy easily by integrating this 2 plus y. Okay. Integrate with respect to y. Okay. And we already did this kind of things before, a few examples previously. So integrate 2 with respect to y equal to 2y. And integrate y times e to the y, you're going to get the y e to the y minus e to the y. Okay. You have to use the integration by parts to do this part, as we already did several times before. So I'm not going to repeat it in here. If you forget, just review the examples we did before. Okay. But it's not hard. Okay. Basically, using integral by parts, let u equal to y and the dv equals e to the y times dy, and then use the formulas, and you get the result y to the dy minus e to the y. So we got the gy. Okay. Once we find the gy, then we can just do the f using the formula. So that's the integral of m dx plus g. So m is just e to the x plus y, and they integrate with respect to x. All right. Remember, specify which variable you integrate. When you do that, you just treat y as a constant, just like you do the derivatives. So when you integrate e to the x with respect to x, you get e to the x itself. When you integrate the y with respect to x, you treat the y as constant. So that's just y times x. All right. Just imagine y is a constant. Okay, and then plus gy. So at the end, f is just e to the x plus xy. You can rewrite that as xy, for y, x plus g, which is 2y plus y to the y minus ey we did before. We got before. So that's the f. And then the solution to the original differential equation is just the f equals c. So that's e to the x plus xy plus 2y plus y, e to the y minus e to the y equal to c. But we are asked to solve the initial value problem, and the initial condition is y of 0 equal to 1. So that means when you plug in 0 for x, you should get y equal to 1. So what we do, we just plug in 0 for x, no, 1 for y into the solution. And the equation should be valid or should hold. So then we got e to the 0 plus 0 times 1 plus 2 times 1 plus 1 times e to the 1 minus e to the 1 equal to c. Okay. Just replace x by 0 and y by 1 in this equation. Okay. E to the 0 is 1. And e to the 1 times 1, just e to the 1. So that cancels with the last term on the left side of the equation. And then 0 times 1 is 0. So we got the 1 plus 2 times 1. So 1 plus 2, which is 3. So we got c equal to 3 from this initial condition. Okay. So the solution to the initial, original initial value problem is just the e to the x plus xy plus 2y plus y to the y minus e to the y equal to 3. Remember, c is 3 in this problem, as we just found out. So that is the solution to the initial value problem. Okay. Any questions for this example? It always involves quite some steps when you do exact equations. There's no easy method or easy way to solve it. You have to follow these steps strictly to find the solution. So what you do, just practice, and do the homework. So you get familiar with those the procedure. Any questions or any thing to share, or have any? No? Okay. The next thing is called integrating factors. So we just talked about exact equations, how to solve exact differential equations by using the procedure we discussed. But there are a lot of problems which are not exact. So suppose we have a differential equation m dx plus n dy equal to 0, not exact. Then how do we solve the equation? Well, it is possible to find an integrating factor mu to make the left-hand side exact. Okay, just like we use integrating factor to solve linear differential equations, as we did in 2.3. Remember, we can solve linear first order differential equation by using the integrating factor. Okay, if you remember. So this time we do the integrating factor again, but this time is for exact equations. And they are all called the integrating factor. We need to find another function to multiply the original differential equation to make the differential equation exact. Okay, so you always need to find a function to multiply the original differential equation and solve it. So we call that integrating factor. Okay. So then we got mu times m dx plus mu times n times dy equal to 0. And if we can do that, we can find the integrating factor mu to make the left-hand side exact. Then we can use the procedure in this section to solve it, as we did the examples. In general, to find the integrating factor mu in this case will be complicated, but there are two special cases that we can solve the problem easily. Okay, so those two cases are: case 1, if m partial y minus m partial x over n is a function of x unknown. So you take the partial derivative of m. Remember, m and n are the functions multiplied with dx and dy in the original differential equation. So you take the partial derivative with respect to y minus the partial derivative of n with respect to x. These are the notations. Then divide by n. If that is a function of x alone, it only has dependence on x, then the integrating factor will be the e to the integral of partial m partial y minus partial m partial x over n dx. Okay. So that's the first case. The other case is if partial m partial y minus partial m partial x over n is a function of y unknown. Okay. So that's the second case. Then the integrating factor will be e to the integral of negative partial m partial y plus partial m partial x over m dy. Okay. So it becomes more complicated. We have a additional step to find the integrating factor. Okay, when the differential equation is not exact, then you try to make it exact by multiplying an integrating factor, and this integrating factor mu is hard to find in general, but there are some special cases that can actually find this integrating factor easily. Okay. Once you find the integrating factor mu, then you can multiply it with the original differential equation so that the equation becomes exact, and then you just follow the steps we discussed previously to solve the equation, because we know how to solve exact equations. All right. So I guess we just do some examples, people may get a little confused, but at this point. So let's just do an example. So let's just find the integrating factor for the equation xy dx plus 2x squared plus 3y squared minus 20 dy equal to 0. Okay, so the first step is always to identify m and n. So in this problem, m equal to x times y, and n equals 2x squared plus 3y squared minus 20. So first, let's see if the equation is exact or not. We know this equation is not exact, but let's just double check it. So what you do is just take the partial of m with respect to y. So xy, take the derivative with respect to y, you treat x as a constant. So then you just get x times 1. So that's just x. And then you take the partial of n with respect to x, and you treat y as a constant. Okay. So then you just get the full x if you use the power rule. Other things are constant. Okay, so it's full x. So obviously, partial m, partial y, and partial m, partial x are not equal. So this equation is not exact. Remember, the condition for the equation to be exact is partial m, partial y equal to partial m, partial x. So let's see if we can find the integrating factor to make this equation exact. Okay. So what we need to do is we need to, check whether we can fit this problem into the two special cases in here. So we need to divide the partial m, partial y minus partial m, partial x by n, or partial m, partial y minus partial m, partial x divided by n. So in which case we can fit in. So when you do that, you're going to find actually the second case. This problem fits in the same case. So partial m, partial y minus partial m, partial x is just the x minus 4x. So that's negative 3x. And if you divide by m, so m is just the xy, so you get the negative 3x over xy, and you cancel x, you get negative 3 over y. And that is a function of y unknown. Okay. And you can easily check if you divide partial m, partial y minus partial m, partial x by n, it will not be a function of x unknown. Okay. If you divide by this function, 2x squared plus 3y squared minus 20, obviously. So that doesn't fit the first case, but it does fit in the second case. So partial m, partial y minus partial m, partial x over m is a function of y, and the integrating factor will be mu of y equals e to the integral of negative partial m, partial y plus partial m, partial x over m dy. Okay. So just use the formula. All right. We already did, partial m, partial y, and partial m, partial x if we plug in. So negative partial m, partial y will be negative x plus partial m, partial x plus 4x. So that's 3x over m, 3x over xy, so we got 3x over xy simplified to 3 over y. So we got 3 over y, in this integral, and just integrate it. And then you take the exponential for the whole thing. So you think you can take out 3 from the integrand and integrate 1 over y. So that just gives you a natural log of y. Okay, we should get the natural log of absolute y in general, but since we just want to find the one integrating factor, you can skip this absolute sign. So we got e to the 3 times the natural log of y, and you can rewrite this exponent as natural log of y to the cube. Remember, using the properties of natural logs or logarithms. So this 3 becomes exponent for the y argument of logarithm. And then because the exponential function and the logarithm function with the same base, e, in this case, there are inverse functions to each other. So when you take the composition of those two functions, you just get y to the cube back. Okay. If you remember properties of inverse functions. So the final answer for the integrand factor in this problem is just y cube. Okay. So that's the integrand factor for exact equations. Then you can multiply this y cube with the original equation on each term and get exact equation, and then use the steps we showed before to solve this exact equation step by step. And I'm not going to show it again here. It will be quite lengthy, as you already see. You already saw it before. Okay. So you can do this yourself at home if you want, but that can be solved anyway. Now we got the exact equation. We just use the formulas, we have, do it step by step, solve the equation. So that's the end of this section. It's a little, it's not very straightforward, it's exact equations. Okay. But fortunately, we already derived all the formulas that you can follow. So hopefully it will not be too challenging for you guys, but still you have to do integrations quite a bit when you solve these exact equations. So that's require the background in Calc 2. Any questions so far about the exact equations? So that's a little more complicated topic. We started from 2.2 separate equations to 2.3 linear first order differential equations, and then 2.4 exact equations. So every time we just get the subject a little more complicated. And you can see how hard it is to solve a differential equation. And we are talking about the first order differential equation only at this point. And those are the equations that we can solve for first order differential equations. And there are a lot of differential equations we cannot solve even for the first order. Okay. So any questions at this point? If not, I'm going to stop this recording.